Hey everybody, this is Larry. This is one of the prompts I saw for the bi-weekly contest 29. I'm gonna put the explanation in the beginning, and then I'm gonna do the live coding of it afterwards. Let me know what you think about this format. I'm still playing with it, and here we. Hey everybody. So for this problem, I actually end up re-recording it because um, initially I thought that the greedy solution worked, and that's what I did during the contest. It turns out that greedy does not work, and there was a case that I'll show later on. Yeah, so that's kind of a weird constraint I think for this problem because n is equal to 15. So it borderlines does not run fast enough for a Python. You have to make a number of optimizations to get it to work in Python. And if you watch the contest video, I actually go into this incorrectly, and there are a lot of people in which read the solutions, especially in Python, they did it with greedy. And I'll show the case where they bricks in a bit. But basically, the idea here is for the correct solution is to use dynamic programming. And what kind of dynamic programming? A sort of a brute force bit mask bit set dynamic programming. What's a bit set, right? So bit set is that say you have a number between 1 to n, or you have n elements, right? And each of them are labeled 1 to n. And then now for each subset, you can just say, for example, 1, 2, 5, 6, 7, maybe 4, just to squeeze it. Then to represent this number as a binary, well, is the first number in the set? Yes. Is the second number in the set? Yes. Is the third number in the set? No. Yes for 4, no for 5, yes for 6 and 7, right? So this is the binary representation of the set. And then now, then the explanation on how to solve this is, okay, well, first you start with every number. So let's say n is equal to 7 again. So now you start with this bit set. It contains every number from 1 to 7, right? And then now you try, let's just say for the example, this is k is equal to 2, right? So then now we start by trying, okay, the f of n, or f of this bit mask, what is the minimum number of semesters that it takes to take all these courses? Well, it is just equal to the minimum number of taking the first two classes, 1 and 2, plus 1, right? So this is taking classes 1 and 2, if possible, in the first semester, right? Or you can also take maybe classes 1 and 3, right? A little copy and paste, a little bit lazy. And then maybe 1 and 4, right? But again, this is only if it's possible. So this is how we do the bit mask one, and you do that recursively by saying, okay, well, let's say we have this one and this one is good, right? Let's say we're here, and well, what is the min of this minimum min semester for this? Well, it is just equal to all of well, for k is equal to 2, let's just say, the first two class plus 1, right? Which is taking classes 2 and 3 if possible in this current semester, right? And again, we dotted, and that's how you do the recursion all the way back down to 0 is your base case, meaning and this is all 0, 7 zeros, no classes left, yay. And that is just equal to 0, right? So f of 0 is 0 because when you have no more classes left, you don't have to take a semester. So that's kind of the recurrence. But of course, that is easier said than done because a lot of the hard time, especially for this particular problem, was figuring out how to do this effectively. And there are a bit of bit mask solutions. I have the code here. Basically, what I did was that I have a prerequisite. Let's relabel this a little bit. And it's really tricky, actually, which is why I don't know, I didn't do it this way during the contest. But basically, the idea is that, okay, for for each possible subset, and I use this. This is a really hard notation to understand in a sense that like it's not a common thing, but it gets the subset of a subset, so it allows you to do 3 to the n times, and then for each of these, so this is a candidate for okay, let's for J it's a bit mask. So for example, in this case, I just go, so like let's say in the let's start from the beginning, right? Or let's just take this one, right? So let's say we're here. I is equal to this thing. This is equal to I, and J is just okay. J just tries every possibility that's a subset of these, meaning that it'll try J goes to 001111, and then it tries to do 001110. J is equal to 001101, and then so forth. ... And it tries these, and then it just checks a couple of things. The first one is that, well, the number of digits that you're trying has to be less than k, because that's the number of classes we're taking. J is the a bit mask of all the classes we're taking, right? In this case, this is 5, so no good. This is 4, no good, so forth, right? And then now let's say we go to some answer in which there is a bit mask of k is less than 2. So this time, okay, it's good, but you can only take classes that doesn't have prerequisites. So what I did is, okay, so I look at for this bit, if we want to take this class, this is what k is. We want to take the kth class. The kth class has a prerequisite. Yeah, so if this is kind of hard, that's why I'm struggling a little bit to explain, because it also took me a while. But if this prerequisite of this class, which is a bit mask, so here we set up for a bit mask for each k, the prerequisite of that class. So that means that, for example, for the power 3, if for a prereq of 3, it's off by 1 a little bit, depending on how you want to count the index. But let's say for this one, it is 3. And if this 3 is equal to, let's say it could be any number of things, but let's say it requires the first 2 class. Well, the first 2 class is good, so you do an n bit on it, and they end up, and the n bit of it should be 0, right? But if for whatever reason, let's say you have any other class in between, if the current I has these classes, that means we haven't taken those classes yet. And if that intersection is greater than 1, or if that intersection is not 0, then you cannot take the ith class. And because you can't take the ith class, we just set this as a not real candidate. And that's basically the dynamic programming recurrence. And then here is just, okay, if the count is less than t, I renamed it t because I used k here. But if we can take less than t number of classes this semester and all the prerequisites are met, we just do the min, which is this current I minus this XOR j just removes the j from the I, and then you do that plus 1, which is the recurrence that we talked about earlier. Again, this is really hard, really tricky to get right, and there are a couple of optimizations here, and the counting you could do with some infix. And in Python, you have to make an additional optimization in which, instead of doing it this way, you pre-choose the k so that you only count the k's that are possible. I don't want to get into it that much, but know that is kind of tricky to get right. Alex has a good solution on that with respect to that. And yeah, that's all I have for the solution. If you're wondering why the greedy doesn't work, let me show a graph. So this is what I drew. This doesn't work because for a graph like this, if you look at the first, if you just do greedy, then if you just do regular greedy by in degree, there are a lot of ways that this could be wrong because and depth as well because they have the same thing. But let's say k is equal to 2, right? If k is equal to 2, your first two nodes may be here, right? These two nodes. And then your second, in your first semester, you take those two nodes. Your second semester, you take this node. And then your third semester, you take this node. And then the fourth semester, you take this node, right? So that's 4. But if you do it smartly, for example, if you do first semester, you do these two nodes. And then the second semester you take, I can't draw it quite easily, but for a second semester you take this node and this node, and then the third semester you take this node. You only need to do in 3 nodes or 3 semesters. Let me color it in so that's a little bit clear. So these two are the same. The yellow ones are the same semester, right? So in that case, both in depth and otherwise, this is the wrong solution. So yeah, so that's why greedy doesn't work, and that's what I did during the contest, to be honest. So some of my commentary may be incorrect on that, but you know, you learn and you keep growing, and that's what I'm trying to do. I think the annoying part is knowing that I did it right. I had the right idea, but I just didn't think that the optimizations would help that much. I guess the test cases were really borderline on timing. I think if they set n to equal to like 12 or something like this, it would make it a lot easier. Just not even that much easier. The implementation would have been exactly the same, but the running time complexity would have been slightly easier to optimize, but also you just won't run into all these time limit addition because you could prove with math that these optimizations would make it fit really easily. Where in this case, you need to be in C++ or Java or something like that to make it fast enough. And in Python, you need another optimization, which is kind of, at least that's I implemented in a couple of ways. Maybe you could do it in Python if you do a lot of other optimizations, but yeah, but that's what I have for this explanation with this problem. Let me know what you think. I'm going to do the live, recording of this afterwards, but keep in mind this explanation. Anyway, parallel course 2. Parallel course 2, Q4. So, yeah, what is this to say about this one? So this one, when I first read this, I was like, okay, I think I understand the problem. And yeah, and I scrolled down. I was like, okay. I when I saw this, I didn't know. I didn't know how to solve it per se. And I was like, okay, this makes sense. This is just standard. You can only take up to K classes a semester. Okay. And then when I saw n is equal to 15, frankly, I was fooled. So well played, problem setter. When I saw n is equal to 15, I thought that I could do brute force. So it turns out that there's, roughly speaking, a 3 to the n brute force. Sorry, not brute. Well, brute force with dynamic programming, with bit masks, and there's a 3 to the n solution, or 3 to the n times n, or something like that. But something that is essentially not fast enough, but barely not fast, or feels barely not fast enough. So I did that for about an hour. If you're watching this, there'll be a link below. I'll skip ahead to the greedy part of the solution, and I'll explain the greedy part as well. Yeah, click on the button. Click on the button below. Hmm. Hmm. A little slow down. Hmm. What is going on? Oh my God. Oh. Oh, poop. It's too long, but I'm 1 and 2 at the same time. Yeah, let's worry about that. I struggled a lot with programming today. Hmm. Mm. It's fast enough though. Just not right. Come on. Still pretty slow, but to the count thing. That shouldn't matter, but still should be wrong though, yeah. One of those days. Why is one never good? Oh my god. What's never good? What? Oh my. Wow. Navi's having a day. Made the same mistake a couple of times. Come on now, really? That's really tight. Let's see. Oof. That was the worst case actually, but guess that's fair enough. How do you do it then? Huh. I must be missing something obvious. Well, a lot of people got this, so I guess I'm just having one of those days where I'm missing the obvious. Well, you thought this would be fast enough, but I don't know. Maybe I do need more sleep. Can you do greedy? Hmm. Still pretty slow. Yeah, let's try greedy, I guess. I don't know. But why would they make it 15? That's the part that I don't get. Welcome back. So for this problem, for right now, to be honest, even for the last 5 to 10 minutes, I was just really thinking about it. Can't be greedy, can it? For n is equal to 15, like they wouldn't give a greedy problem if n is equal to 15, right? So that was my like I was out of ideas. I just couldn't think of anything else because I was like, okay, if it's not brute force, it has to be greedy or some sort of greedy. But I just couldn't. I was like, 15, n is equal to 15. This is, this has to be brute force, right? So I did really spend a long time convinced that it was not greedy because of n is equal to 15. I thought maybe there's some clever 2 to the 15 solution of something. But after an hour on trying to figure out dynamic programming and brute force and something like that, I was like, okay, look, Larry, you ran out of ideas. You don't. I mean, you just don't have anything else, right? Like if greedy doesn't work, fine, but you should at least try greedy because it might work, and then you tried everything, right? And I already at this point, you might not have seen me code everything, but I was in my head. I tried like for an hour, like different things to kind of get it to work, and I couldn't get it. So after that, I did greedy algorithm, and I explained this either later or before in the explanation portion. But basically, the greedy part comes from figuring out that okay, given the longest path of a course or like given the longest path of this graph, that will always be at least the minimum length, right? But we can't like that is the smallest minimum length of minimum semesters. So I was like, okay, well, I guess we could just greedy on that because we always want to take the longest path or the node that leads to the longest path. That's part of the longest path because why not, right? Because you have to take that class before all the classes that depends on it on this longest path. So basically, that's what I did. I did have a little bit dynamic programming on getting the longest path, as you see in this function. Actually, maybe I forgot. Actually, I guess it's a depth first search. You didn't need to cache it. I think I just forgot to cache it because I thought that I would just cache it. So actually, I'm glad that. Whoops! I only noticed this now. So in the explanation portion, I actually forgot about this. But yeah. So that actually made the complexity a lot more expensive, but somehow it still passed. So I'm happy about that. But yeah. So given so I was just thinking a little bit of what do I need to sort it by? Do I need to sort by the out degrees? I was like, no, I mean, not really, because if the out like even if a node has multiple or like a lot of out degrees, you still have to query it in some order because the longest path is the thing that matters the most. So what I do now is that for every class that we can take, we sort it by the longest path by putting in a priority queue, and then we just take the top k elements every time of the priority queue. So that basically we're taking k courses or up to a courses every time, and then every time we take those k courses, we free up new courses that we can take. And this is basic topological sort. But I actually didn't know that you could do greedy this way, so I'm happy to kind of learn about this today because I really thought that it has to be dynamic programming or brute force. Maybe I just haven't thought about this problem in a long time, topological sort, beyond the bare minimum. So I'm happy to kind of be reminded about this. yeah, at this very moment, I was like, okay, do I need another key to figure out what to sort this by? I was like, no, actually, for the heap, I just need the longest path, I think, for what I said about the out degree earlier. And then now we take we just go through the entire list and yeah, and we just take K courses at a time. Yeah. But yeah, but that's pretty much all I have, to be honest. Yeah, because as soon as I did this, I clicked submit and it worked, and I stopped thinking about it. It was very sad, but yeah, still, it is what it is. Yeah, let me know what you think. How you did on this problem? How do you do on this contest? Well, I guess the other guy is still talking or going to talk, so listen to him, and bye bye.